Hello everyone. The study that our group chose to do our research on was post-exercise repletion of muscle energy stores with fructose or glucose mixed meals. Some background on our study is that adequate recovery of muscle energy stores is critical after exercising and is largely dependent on nutrition. It is also important in maintaining muscle glycogen and has been considered a major challenge for endurance athletes due to its limited content. Therefore, consuming foods or beverages that contain glucose or maltodextrins is crucial to improve post-exercise muscle glycogen repletion. The majority of studies that have been done in the past have found that there is a lower muscle glycogen repletion after fructose ingestion than after glucose ingestion. Also, during those studies, muscle glycogen synthesis was monitored almost immediately following exercise. Fructose, on the other hand, is mostly metabolized in the liver, unlike glucose, and it was also shown to have a big part in restoring hepatic glycogen after exercise. Also, a high amount of fructose is also released as blood glucose and lactate from the liver. Both fructose and glucose can differently affect muscle and fat storage. This is where the intramyocellular lipids, also known as IMCLs, come into play. IMCLs represent an alternative energy source to muscle glycogen, which can be mobilized during exercise. This then brings us to the hypothesis of this study, which was that the consumption of fructose might stimulate IMCL repletion more efficiently than glucose consumption. The purpose of this study was to compare the effect of isocaloric liquid mixed meals containing fat, protein, and either fructose or glucose on the repletion of muscle energy stores over 24 hours after strenuous exercise session.
This study was classified as a double-blind, crossover-controlled, randomized clinical trial. The participants consisted of 8 male endurance athletes around the age of 29 with a peak oxygen consumption of around 66.8 milliliters per kilogram per minute. These participants were studied twice throughout the experiment. The two main things being assessed in this experiment was glycogen and IMCL concentrations in the vastus muscles. The variable in this study included 4.4 kilograms per gram of either fructose or glucose in the mixed meals that the participants consumed. Energy metabolism was evaluated, and also IMCL concentrations were measured again after 24 hours. This study started out with 11 participants, but then dropped to 8 because 2 participants had gastrointestinal symptoms during the fructose condition and had to drop, while the other participant that dropped didn't comply with the diet. During the beginning stages of the study, the participants were asked to perform a physical fitness test that went to exhaustion. Before the start of the altered diets, participants were given a control diet that consisted of 55% carbohydrate, 30% fat, and 15% protein. They were also told to only drink water. On day 1 of the study, participants performed 1 hour of endurance exercise, and then on day 2, participants were asked to remain sedentary. Day 3 of the study had participants perform constant load cycling. Also on day 3, the participants started their experimental isocaloric mixed diets that contained either fructose or glucose. In order to evaluate the effects of these diets, plasma metabolic markers and energy metabolism were monitored 6 hours after dinner and after an overnight fast. The researchers of this study used non-invasive measurements for measuring IMCLs and glycogen concentrations. The machine they used to measure the IMCLs and glycogen concentrations was a 3 Tesla whole-body scanner. When preparing the meals, both fructose and glucose contained the same total energy and macronutrient composition. On the 4th day of the experiment, the metabolic effects of the experimental diet were directly assessed. The ways they assessed the metabolic effects of the mixed caloric diets were blood analysis, which measured the participants' FFAs, triglycerides, glucose, and lactate. Respiratory exchange measurements and urine analysis were also performed in a fasting state. On the 5th day of the experiment, participants were asked to perform 3 hours of prolonged cycling or until exhaustion. During this test, blood samples were taken through a forearm vein cannula. Also, energy expenditure, RER, and substrate oxidation were measured by indirect colorimetry.
There was one outlier that stood out in this study. This participant's IMCL and muscle glycogen concentrations were higher between day 4 and 5 of the trial. His data did not follow the trend which all other participants followed. The varying data was attributed to a failure to comply to the dietary instructions given by the researchers. Therefore, this participant's data was excluded from final analysis. The data from 2 participants in the fructose group was also excluded because of gastrointestinal symptoms caused by the fructose mixed meal. They were not able to finish the study, therefore their data was inconclusive. Researchers hypothesized that the consumption of fructose might stimulate IMCL repletion more efficiently than glucose. What they found was that both fructose and glucose, when digested with proper fat and protein, leads to similar concentrations of IMCL and muscle glycogen. The issue with the fructose group was that half of them could not finish their trials, while everyone from the glucose group was able to. While muscle glycogen was similar between both groups, the muscle's energy supply systems were negatively affected in the fructose group.
It was found that diets higher in fructose are more likely to hinder performance and increase fatigue due to low energy supply to the muscles, although there were still similar concentrations of IMCLs. A high fructose diet during recovery post-exercise is not ideal to significantly maintain exercise performance. A balanced diet consisting of fat, protein, and where glucose and fructose are both consumed is most efficient in repletion of muscle energy stores and IMCLs. Fructose alone lowers the rate of glycogen synthesis of the total body, which leads to impaired athletic performance.